Hi everyone, thanks for your attention to our work. In this video, we will introduce an effective Bayesian optimization method based on Poisson process. In the black box system, we can only observe the noise's response of the input signal without other function information of f. In some scenarios, we even cannot directly access to the absolute response y, but only some relative response of the input, such as preferences or rankings. Bayesian optimization is an efficient method to solve such a problem, especially when a black box function is expensive to be evaluated and has no closed form expression. It alternately trains a circuit model to estimate the response surface of the black box function based on the observed samples, and suggests the next query based on an acquisition function balancing the exploitation. Popular surrogate models for the first step include random forest, tree structure Poisson estimator, Gaussian process, aiming to estimate the distribution of function values for each candidate. Classic acquisition functions for the second step include expected improvement, Thompson sampling, and upper or lower confidence bound, aiming at the exploitation trade-off. Most of the prior build methods attempt to build an absolute response surface of a black box function based on observed function values, and few have been explored to build a relative response surface. Compared to absolute metrics, relative metrics can have the following advantages. First, relative response such as ranking has better practicality, since the information about candidate preferences can be more easily acquired than raw values, such as sports game and recommender systems, where only relative response can be provided by pairwise comparison. Second, relative response is more robust to noise than absolute response, since relation between candidates is hard to be disrupted by noise. In this work, we also analyze the better robustness of rankings against absolute response on the Forrester function under the common additive Gaussian noise assumption. Specifically, we sample 15 queries, add various degrees of Gaussian noises to the observations, and capture a response surface with a value-based model and our ranking-based model. In order to fairly evaluate the robustness to noise, we set prior to noise at 0 when training the models. We can see that the ranking-based model performs much better than the value-based model. Third, relative response has better transferability, since they are usually comparable among multi-fidelity metrics or evaluations across different datasets for the same candidate. In this work, we assume the rankings of X over two disjoint areas are independent, since the function f is black box, and propose to model the ranking of X over set S as a Poisson process. The probability of X ranking K over the whole space X is derived as a second equation. We utilize MLP to predict lambda, which can be trained by maximized log likelihood estimation through SGD. Hence, the predicted probability distribution can be derived as the third equation. To sum up, we capture the ranking of samples via Poisson process. The variance of a Poisson distribution equals to its expectation value. Therefore, applying the vanilla LCB acquisition function to our method will lead to an over-exploitation issue. To this end, we introduce the rectified technique and introduce a rectified upper confidence bound named RLCB for our method. We use a predefined contour parameter Q to restrict the lower value to a threshold. As above, epsilon is a uniform random variable for reparameterization, and Q is a predefined contour of the number of samples. The threshold can be adaptively adjusted during the build process. The experimental results of the ablation study on Rosenbrock benchmark is shown in this slide. Inspired by AI, we introduced ERI to maximize the expected improvement on ranking over the worst tolerant ranking K subscript M. We set K subscript M equals to 5 by default. It indicates the expected improvement of the ranking over X compared to the top K subscript M, not only for top 1 in vanilla EI. We also apply the rectified technique to the ERI acquisition function. The experimental results of the ablation study on Rosenbrock benchmark is shown in this slide. To verify the performance of our method, We conduct experiments on both simulated functions and real-world benchmarks, including HPU and NAS. This slide compares the performance of our method with other classic BU methods, including TP, SMAC, and GP on the simulated functions. Although the standard GP temporarily outperforms others in the early stage, our method gradually catches up and takes the lead till the end. This slide compares our method with advanced Bayesian optimization methods and random search on HPU bench, showing that our method achieves the best on all the 4 datasets. We run each method for 10 times and plot the trend of minimum regret during the BU procedure. This slide shows the performance of various black box search methods on Mass Bench 201. Our method achieves the best performance on the 3 datasets. Thanks again for your attention. You can get more details in our paper.